I guess almost a decade ago, we kind of started revisiting the original idea of using flashlight and fire as a way of our primitive wireless communications, many, many centuries ago. And the idea is that the photonics, both in integrated form and systems and networking, has made leaps of progress in the last 3 decades. Therefore, there must be a possibility that we can offer a viable alternative to really truly broadband, in the sense multi tens of gigabit per second connectivity using optical techniques. So we started exploring these in a systematic way, trying to look at ways of addressing some of the challenges in photonics becoming a wireless alternative. Let me walk through some of the talks, but I will leave lots of references for those who are interested in to follow deeply about specific work. So I'm going to walk at a very high level, but feel free to reach me if you need any specific details. Let me see whether it navigates to the next slide. So a very quick walkthrough in terms of the outline, but I might change a few things here and there. A quick dive into free space optical communications. Again, a pointer if you wanted to look at much beyond the Indo optical wireless communication, which is going to be the focus of this talk. But then I will quickly dive into looking at optical wireless communications from a system architecture and the key technologies that will enable us to do that, and then present you some of the work in optical network architecture that can seamlessly work between optical and RF and terahertz communications, and as an alternative to potential 6G type of communication configurations. Hopefully, I will have enough time towards the end to provide you some reflections on where the challenges are, where we need to go in terms of pushing this technology to adoption. In the context of where we fit in, as you know, you have had lots of talks in this space. So we already know fiber is a major player in the networking today. Where we see a role for optical wireless is in the areas of both in the edge and from interconnections between parts of network. For example, from ground station to space, it's going to be a critical technology for the delivery of connecting the unconnected in the world. It's still about 60% of the world's population is hungry for a viable internet connectivity, and they've been denied of that so far. So there may be a potential role for free space links in that. There's also potential for drone-to-drone or a space platform communications. But this talk in particular, I will focus about much short distance, very high bitrate communications in in-building or extension of fiber to the home networks. For those who are keen on understanding where the free space optical communications have been pushed for, as I mentioned, from ground space to ground to space to in-space connectivity to backhaul between base stations, these have been explored. Here is a kind of review article recently appeared, so that may be a good point for those who are interested in this, understanding it. And you can see the plots of data rate on the vertical and the horizontal log scale in terms of kilometers. So you can see transmitting reasonably broadband data over a relatively long distances using either point-to-point pencil beams. We have made lots of progress over there, and there are commercial players providing these platforms today. Whereas our focus is about providing an indoor high-speed connectivity, and you can think of this as a building block in the same way as a Wi-Fi access point may look like. A ceiling-mounted and optical transceiver assembly that gives you the network connectivity. A similar optical assembly will transmit and receive from the user end. And in this case, we are talking about a diffused or a pencil optical beam between the optical assembly on the ceiling to the optical assembly on the user device, forming the connectivity. In terms of traditional connectivity, this is called diffuse beam because the beam is a cone of light. And if the receiving assembly is within the line of sight of that assembly, you can establish wireless connectivity. Of course, the optical aperture of the receiving assembly is only able to select a small portion of the signal transmitted from the ceiling assembly. In terms of those who are in the more communication network or systems modeling, you might be wondering what is a key type of impairments that would be affecting these type of things. In the case of where you may have a secondary reflections, you might have multipath fading. This is very rare in the case because most dominant signal is the line of sight signal. There may be a turbulence due to air conditioning or heaters playing, but again, we observe very little effects of turbulence. Essentially, turbulence induced refractive indexes, and therefore that changes the channel behavior. It is very rare in indoor settings. The most dominant impairment is really the presence of background light, which is always present in most built environments. In terms of the windows or the spectral regions of interest to us, and as you would know that, I'm sorry that I moved that slide, this red arrow on the left should be in the 0.8 in this part of the window. And the other one, of course, due to the presence of optical amplifiers is these windows. Of course, these two windows can also be possible, but currently we focus on this window around optical amplifier areas and also in the areas where near visible area. The advantages for this is that we have pretty much unregulated bandwidth. We can simply dial up or down using the different domains, exploiting the photonics to the full extent in terms of wavelength, in terms of spatial multiplexing. And it's also maybe ideally suited in environments where RF is denied. And there are some disadvantages in the sense there can be limitations on the power that you can transmit due to you establishing a cone of light, and then you need to limit your power to the laser safety standards or safe power levels stipulated by different standards. And most important restrictions is because it's a line of sight. But if you do look at the alternatives for providing multi tens of gigabit per second connectivity, all other technologies have these limits, whether you're using millimeter waves or whether using terahertz signals or optical signals, they all line of sight. So within the optical wireless communications, as your previous speaker would have highlighted to you, there are broadly two major classes of networks. One is used on incoherent sources like light emitting diodes as sources of light and forming coverage by establishing multiple LED transmitters that can establish cones to cover your coverage area. And again, those who are interested in that, using LED for visible light communications or even invisible light communications, this is a very good paper by Li-Fi work coming out of Henry Hertz Institute. And also you had another a speaker also earlier presenting that work. In our work, we were motivated by the fact the fiber to the home or fiber to the building networks can be easily extended by using optical wireless transmission. So our work is about optical feeder network from a central office. We feed very much like fiber to the home, potentially using WDM or passive optical network technologies. And then a ceiling mounted transceiver simply establishes cones of light, and those cones of light can be steered towards any specific coverage location in the network. Again, those who are interested in an overview of the work, this review paper came out this year, might be a good way to capture some of the work that we've been doing. So in our work, we were trying to explore a laser-based optical wireless system that can be delivered via optical fiber distribution network. So we started addressing the key pieces of puzzle in terms of building this technology towards a viable networking alternative. So initially, we looked at how we can steer and direct beams to any arbitrary location in the coverage zone. Then we looked at how we can achieve localization of users, because if you wanted to provide mobile connectivity, we need to know where the more users are so we can direct the beams towards that. So I will briefly mention about the localization directly at the optical domain. Then we recently explored ways of dealing with the blocking of optical beams, because remember, this is a line of sight, and therefore it may be impacting, in some cases, the beams may be blocked, and therefore how we overcome that. Then I probably will take you to optical networking architecture that we recently proposed, where we can integrate all other possible alternatives like the terahertz signals or a millimeter wave system, and our approach to photonic-based wireless all can coexist within an optical feeder network architecture. We're working on a few other challenges in terms of mapping these system concepts to planar circuits, but we yet to really break through some of those challenges as yet. So let me dive into key areas. So the first area is how we actually set up this optical wireless. In our approach, we use a fiber feeder network. So the fiber comes to the ceiling. It has these optical assembly. Essentially, for example, in the downstream, we take a fiber and then mount a lens on a voice coil, which can be electronically controlled, so that by changing the fiber to the lens distance, we can establish cone of light with a variable controllable diameter in terms of coverage. Then we pass it through a pair of steering mirrors, essentially MEMS mirrors, and that allows us to steer the cone of light to any coverage area that you would like to establish. And so the central office is the one that controls the transmission. Ceiling mounted access point looks like this. And in the reverse direction, you have a range of lenses that allows us to collect the signal from the user back into the fiber towards the central office. If you zoom into the transceiver assembly, this is how it looks. In the upstream direction, we use actually VCSEL because it is much more lower cost, and in the upstream direction, maybe the data rate may not be that high, so we can actually achieve a few gigabits transmission using this way. But in terms of from fiber to the free space arrangements, exactly the same architecture as I mentioned earlier. In the downstream signal, we use a parabolic concentrator, CPC, to map a slightly wider aperture back into a narrow aperture of a photodiode, and then amplify to complete the receiver. There are other groups worked on an alternative way of steering the beams and setting up the coverage. In our case, we're using electromechanical systems to steer and establish the cone of light to complete the very high bitrate communications. In this work, they have used a 2D grating-based beam steering, where the grating remains fixed. By shining a light with the wavelength that is controlled, we can then use the grating's reflectivity as a function of wavelength to be able to direct the particular wavelength at particular locations. So the only challenge of this one is you need to use a large number of wavelengths in order to be able to cover different areas of this. But it is very fast, and there has been really high capacity systems have been demonstrated using this approach. So back to our work, and here is for example, we use a 1550 in the downlink because we can take advantage of the optical amplifiers and have about 7 milliwatt of power that we radiate out from the lens. And in the downlink, we use a simple on-off keying, but of course you can use higher modulation scheme to boost up the speed higher, or you can use WDM to create multiple wavelengths at much higher. So we've demonstrated up to 80 gigabits per second capability by using WDM. In the upstream, as I mentioned, we're using VCSEL-based transmitters, and in this case, we're using an advanced modulation method, again, much simpler, such as 16 cap, in order to take advantage of few hundred megahertz bandwidth of the VCSEL, but achieve about a few gigabits of uplink connectivity. This is over a 2-meter indoor kind of coverage areas, and we assume we will be able to take advantage of the FEC. So you can see here in the downlink 10 gigabit, you can see it's getting closer to well within the FEC limit to achieve the error-free transmission. In the uplink, of course, we don't need to even achieve, in the uplink here in the 16 cap modulation here, and the downlink, because of the amplifier, we have much better power levels involved, and therefore we can get much better performance in the downlink. In the uplink, the cascaded insertion losses is high at the moment, and that's partially related to this, but it's still with the FEC, you should be able to get back this error rate. So this is just the idea of how we use optical wireless to establish a connection. Let me now switch that to see how we localize uses so that we can direct the beams to the right levels. So if you look at the optical power transmitted from the ceiling mount, the transmitter towards the user's only usual working plane, in the 2D system, you can map the received optical power to the distance away from the transmitter, and that power level will depend on this formula. If we have a way of setting up this transmission system, and by controlling the tilt, we can make multiple measurements with the multiple offset, and we will be able to localize the user within the 2D quite easily. So what we do is we establish a cone of light, which is a much wider beam initially, so that we can visible everyone and send out a request message. Then we narrow down the beam and then scan to search for where the users are. And as we do that, we can actually recognize the users in particular location, but also the way that we scan that allows us to give us enough measurements to be able to precisely determine the location of the user using the algorithm. And so with the combination of the formula and with the search and discovery algorithm, we can actually, and by controlling the tilt mechanism, by tilting once and then making another tilt and then making another set of measurements, and by repeating that process, we can actually determine the X and Y locations of the receiving end quite easily. And here you can see we can get about few centimeter accuracy in terms of localizing, which is very good for most mobile data applications, because even our physical dimensions are much higher. Even if you think about a robot moving around, it's probably most likely a few centimeter diameter. So getting an accuracy within a few centimeters with a few centimeter cone of light beams, that should be more than enough in most cases. How do we localize the 3D in terms of the height as well? Again, we do that by setting up a reference plane where we know at a known height, we know the power distribution formula. And then we also work out an arbitrary plane where the user is. And by taking these, triangle that connecting the reference plane at height h0 and unknown height hu, we can actually again go through the same formula. By taking enough measurements, we will actually be able to, you can go through the algorithm in the paper, you will see that we will be able to work out the actual height hu once you know the reference calibration height h0 and certain parameters of this expression, then we can actually even localize in 3D. And this is experimental results from a 3D localization. As you can see, in the XY few centimeter as before, in the height slightly a higher error rate because of that reference calibration, but still within few centimeters. So for a cone of light with the coverage around a few tenths of centimeter, your accuracy is within few centimeter, then it should be possible to establish wireless connection in a mobile context. It then have a problem. Okay, we can localize the user, we can deliver the high bandwidth connectivity, but what happens if the line of sight gets interrupted? Then you will have momentary loss of connectivity with your user. So we started looking at ways of exploiting spatial diversity, which is well known in the communications in the RF domain. We again borrow the concepts that has been well established in the RF domain and try and see how we can achieve that. So in the case of spatial diversity, the idea is that we use maybe 2 transmitter, single receiver idea. So it's a meso architecture, a multiple input, single output kind of idea. So in this case, we have 2 transceivers which are spatially separated. So if the line of sight from one of the transmitter is blocked, there is likelihood that the other transmitter will still be visible in a line of connections. So we then explored the most 2 popular coding mechanism. One is known as repetition coding, where via the 2 independent channels that you have to reach the user, you pretty much in adjacent symbols, you simply transmit the duplicate same information on both channels. And then you combine the receiver actually receives the combined signal of both channels, and you have the repetition decoder that are able to decode this with some knowledge of H1, H2, we can decode the information. And also another popular form of spatial diversity coding is space-time block coding, or Alamuti type. And in that, basically, we transmit conjugate symbols over adjacent symbols on the second channel compared to the primary channel. And we then experimentally explored which of these things might be better for our given context. So here is an experimental setup operating at 10 gigabit on-off keying with both repetitive and repetition coding and STBC coding. And so we're using a 2x1 meso architecture with a 1550 nanometer laser, which has a diffuse beam with about 16 degree of angle. And we had to incorporate the background light, which is as an impairment. And we have the lens to fiber coupling interface is used to establish this setup. Here you can see the experimental results from repetition coding and STBC under equal power between 2 channels. That means both are visible, and unequal powers when maybe one may be partially or fully blocked. And you can see here the repetition coding is experimentally slightly more robust than the STBC, and therefore the repetition coding can be utilized to establish spatial redundancy as a protection against potential blocking of line of sight optical wireless links. So here we now move to one of the key areas in the context of the architecture, in the sense, it's okay to have wireless communications which are very fast in the optical domain, and we can have other mechanisms to overcome some of the challenges. But we know the wireless, there has been a number of alternatives to do that. In wireless, what we have so far been able to see is that, for example, if you take the current Wi-Fi protocols, which are contention-based protocols, if you try to just simply dial up the speed, the Wi-Fi doesn't work as good as you would expect. In fact, it is very poor. Even if you have 10 gigabit bandwidth, the Wi-Fi protocols, because of the contention mechanism, it actually will only be able to get up to 50% of the 10 gig capacity. And so we realized if we wanted to use optical wireless as a high-speed alternative, we need to optimize our currently available wireless transmission protocols. That kind of led us to think about the architecture where we can manage these things. So in a very simple work, we opened up the Wi-Fi protocol and optimized the certain parameters in the protocol. We were able to get almost 80% of the capacity, that is 10 gigabit, even when the network is loaded up with number of users. So that kind of motivated us to look into a new type of architecture to have a very high speed data connections using the optical wireless networks. And we also recognize in the access domain, as we move towards 6G, it is quite possible multiple technologies need to be harnessed in order to provide that connectivity, and any networking architecture should be compatible with different last meter connectivity solutions. So in this first case, as I mentioned, some of the problems in the wireless protocols, for example, is that it uses carrier sense multiple access as a collision avoidance mechanism. So what it does is it does have a contention window, and normally this contention window is fixed in the protocol. So when there is a contention, you just simply wait and then come back to it. And this fixed contention window can actually cause significant throughput degradation when you have large number of users want to have that capacity into the network. So we actually then looked at how we can change this contention window to be suitable for as a dynamic basis, so that it, rather than being fixed, if there are fewer users, then we can have a different contention window. When there is some traffic, a lot of users, we can use different contention window. Similarly, if there is a high quality service like video or AR, low latency connectivity, we can give them preference to those users compared to the others. By playing with this contention window, we can fully utilize the very high speed nature of the optical wireless. So without going into details, I'll show you what it is essentially what we're doing is a simple dynamic the contention window tuning. So we're simply changing that window where the contention is managed by looking at what is the current throughput. So it's a kind of machine learning, very simple level of learning built into the algorithm. So essentially, we're checking the throughput. If the collision rate is high, we check the delay and then basically increase the contention window so that we wait longer before we rejoin. But if the throughput is not, when there is not many people are trying to access it, we can have the contention window low, and therefore we can have a much better reconnection approach. With this, you can see here with the conventional Wi-Fi style protocol, you can see it never goes beyond half the throughput of the maximum 10 gigabit possible. And with the optimization of the algorithm, we can go improve. So essentially, the key message here is not the dynamic contention things. Key message is that the current protocols that we explore for bandwidth, the local area networks or indoor access networks cannot be simply trusted to provide very high speed by simply throwing bandwidth at it. They are not designed for this, therefore they need to be redesigned. And so this is another one actually showing that the delay can be substantially reduced for most of the traffic as the because of that optimization that we did. That kind of led us to motivate that we need to be rethinking about the architecture for optical wireless rather than just simply thinking the physical layer independent protocols such as 15.15 kind of families cannot be directly applied to these networks. And so in this case, we came up with a flexible optical wireless network architecture, which has a separate control and data plane so that we can actually support very high bitrate communications. So it's not just us who were motivated by this. There were other projects in Europe was looking at optical wireless and then trying to recognize the same problem that protocol need to be redesigned if we wanted to realize very high bitrate wireless communication links. And so obviously, as with any network, when we have a higher bitrate systems, if your control plane, that means how you manage that layer, and the data plane, which can burst out very high speed, operate using the same channel, which may be subject to line of sight connection issues, blocking issues, then you can have a lot of periodic disruptions in this transmission technology, which may basically damages your throughput. So there is one recognition: we need to have separate control and data plane. Second one is that as we go forward, everything is going to be software defined. As a result, we need to make sure optical wireless layers also can be managed in a software defined networking context. And this work has been explored both in the case of optical wireless with the lasers and also visible light communications, because the challenge remains the same. So let me quickly go through the architecture that we proposed. So if you zoom into the coverage zone, we have an access point which is ceiling mounted, which can actually deploy wavelength division multiplexing. That means it can set up cones of light using multiple wavelengths. We have a control plane beam, which is indicated by the yellow here, which is a much wider beam. The idea is that by using low data rate, wider beam, all the users remain visible to the network. So they can be controlled, signals can be exchanged without any line of sight issues. And then we have narrower beams, which actually can direct data channels at much higher data rate. Because they are narrower beams, their data rate can be higher because within the given power levels, it can actually get better connectivity if the beam is narrower beams. And these beams could be optical beams, and then in that case we will use one wavelength for up, one wavelength for down. It may have different sectors. That means it may have different coverage zones in which the beam could be directed, or it could have in each of the beam maybe millimeter wave beam, or it could be terahertz beam. The only thing changes is the transmitter, physical transmitter that establishes that cone of signal, which could be light, which could be terahertz, which could be millimeter wave. And the ceiling mounted transceiver has almost like a one-to-one link to a remote node, which is where all the processing happens. So the access point has a simple transmit-receive pair that connects to the central office, where all of these access points have a virtual implementation there. So we can manage and control everything there. From there, it basically delivers the wavelength to the ceiling mounted transceiver. So by having an ability to virtualize these connections, depending on the need, we can turn off certain things. Depending on the bandwidth needs, we can turn off that. So you will see these colored boxes in the gray area, essentially a copy of individual access point in the optical domain. And there is a one-to-one connectivity to the access point from the virtual access points there. And the virtual access point is where the resources are decided, managed, so everything can be software managed, so it is compatible with software-defined network. You can design the protocol in either contention-based or contention-free, and both of the protocols we have published. Those who are interested can actually have a look at it. So essentially, we have a very high capacity optical network connecting the central office to the access points, which is optical. And from the access point to the sectors, it can be optical using our technology, or it can be a terahertz or millimeter wave link, but it will connect to the central office via optical feeding. So this allows us to use any physical layer technology in the future access network architecture. And here is the details a little bit, and it may be harder for you to see it through the screen, but again, I put the references there, and you can actually download. This is there's an invited paper in the Journal of Optical Communications Networks, just came out, that actually goes into the details of the design. Essentially, it's nothing. The virtual access point in the central office is, control plane is separated for each of the sector. and control plane is here, one common tool in the yellow, and the blue boxes are for each sector. There is a one interface to both upstream and downstream interface goes through that. And you can actually have queues in there to separate high bandwidth, low latency services versus basic data services. Similarly, on the user end, it goes to the access point, and then via optical wireless, it goes to the user. And the user stream, you can see the control plane is separated again, the yellow path, and the blue path separates the data plane. So having separate control plane and data plane, the users always remain visible to the network, and then you can burst out when the bandwidth is allocated at full capacity to what the physical layer technology can allow you. And so in any other normal network, the router will forward the packets to the classifier, and the classifier will work out based on the priority, and then it will basically forward, depending on the using the queue, it will actually forward it with a high priority or low priority to complete the links. And the same reverse happens from the user all the way up. So you can see it's almost symmetrical implementations from all the layers, from application to physical layer, from the virtual access point and to the user. You can see it's the same reverse arrangement is there. So we compared this using an optical wireless access point with the 1 kilometer connecting to the central office in the discrete event simulator NS3, and similarly we also compared that with the Wi-Fi 6 based Ethernet feeder network and checked which one will work better. And similarly we have also modeled the terahertz link in a separate work. And you can see here, as we expected, because of the split plane where control plane can manage it, then we can actually have a network that actually has maximum throughput. So you can see here 0 to 10 users go up to 10 gigabits. So each user can get up to 1 gigabit per data per second. With our network, you can see we can reach the maximum almost maximum 10 gigabits. So this is now 8 gigabits maximum capacity is reached, and it's full duplex. And we also have other modifications, half duplex, and you can see the blue line, which is the Wi-Fi network, and as you can see, it doesn't do well to give you the capacity when multiple users are asking. So this highlights the problem with the Wi-Fi based designs. This also highlights the way that we have overcome to be able to establish high-speed architecture that is capable of working at 10 gigabits and higher. And similarly, on the left diagram, you can see here that the bottom diagram, you can see this is a delay versus number of users. And as you can see, with our network, we can actually keep the delay almost low here at the lowest delay. So it is the lowest latency transmission possible. Everything else after 5-6 users, you can see the latency really suffers a lot because of the issues that I talked about. And you can also implement full duplex in the sense you're using separate wavelength for up and downstream, or you can use half duplex in the sense same wavelength is being time division multiplex and using it. And we looked at how it does. In the half duplex, of course, you will expect the maximum capacity will be half because in one direction, as these green dots indicate here. We also looked at, we need to establish the control plane using the signal. Most of the optical sources are Gaussian, so you will see this Gaussian power variation across the beams. So in this case, you can see here, there is one control plane in the yellow in circle here, and there are 4 sectors in this which are data planes which have separate beams here. And we model various power distribution And initially, we started with Gaussian beam profile and then investigated whether how this can operate. Recently, we have actually developed some optical means to have uniform beams across, uniform intensity beams across the cross section. That way, it doesn't matter where the user is, they will get constant performance. So we can actually investigate that as well. Again, we show our architecture can give you the best performance compared to any other architecture currently available. Again, we model the users walking, moving within the coverage area and being able to see whether they can maintain the visibility with the control plane while they also being able to get highest data plane. There is a slight difference between the way they walk, either random walk or random waypoint, but effectively they still perform high performance network using our architecture. Let me maybe, because of, I think I wanted to give you some opportunity for questions and answers. So let me wrap up here with a reflection on some of the challenges that I see in optical wireless. The optical wireless is limited by the power that we can transmit in the air in the living area, and different standards specify us how much power that we can. Remember, these standards were written once when we had point sources, whereas now we can set up a cone of light and the light may come out of an aperture which is wider than one spot. Therefore, we can interpret the standard differently and break to some extent. We can improve the power through that, but largely it is limited by amount of power that we can transmit in a way that users are happy with it and they are safe and nothing can be done. But because of the availability of the optical amplifiers, the 1.5 areas and the near visible spectrum seems to be the most promising opportunities in terms of immediate exploitation. One of the challenges in the contrast to alternative techniques is both millimeter wave and terahertz signals can be integrated into planar form much more easily into a very small footprint. Whereas when it comes to optics, at least so far, we are constrained by telescopic arrangements and bulk optic lenses and things. So of course, we are now shifting our work. How can we map our architecture to a planar form using nanostructured materials? And I see some of your capabilities also in this space, which will be interesting to see what type of nanostructures you guys are working on. Because I think that is the only way we can then realize optical wireless transceivers that are genuinely planar and optical apertures that are almost compatible like millimeter wave antenna arrays. And I think that's the direction where we like to explore. So we're looking at ways of achieving nanostructured interfaces that can couple light and manipulate light and then establish, at least at a given angle, apertures that can either radiate light in the way that our architecture needs it to work, and similarly apertures that can actually focus light received from the transmitter and achieve high bitrate operations. So that remains a fundamental challenge. I know there are a lot of work now in nanostructured apertures that can couple light in and out, but where we need to go is that need to be compatible and integrated with both active sources and photodetectors in a way that we can complete the wireless link. So in summary, I guess as an alternative wireless technology, photonics is actually capable of easily meeting the bandwidth requirement. It also can easily meet the core requirement of mobility, is that you need to know where the users are if you want to have a beam steering communications. And we also have some ways of overcoming the blocking of beams or the line of sight connection disadvantage. And we're starting to realize how to realize them in an optical networking architecture context by using split plane making sure all the users are always visible to the network by having separate control plane and a data plane, and of course, making sure this technology is software definable. But challenges still remain. Can we map this onto a planar optical transceivers? And I think that's where the future explorations of these is going to go. With that, I might wrap up there and then give you some time to ask questions.